SMJP 1022 Material Science, Chapter 7 Carbon Steel. In this chapter, we will divide into two parts, which is part A, which we covered equilibrium diagram of iron carbon, and the second one we will cover at part B. We have a heat treatment of steel and time temperature transformation diagram, or we call it TTT diagram. So in this chapter, we will cover of the ferrous metal. So before we go through for the ferrous metal, we will try to look at the engineering materials, which covered all metallics materials and non-metallics material. So for the metallic material, we have ferrous and non-ferrous. Actually, the ferrous is a base content of iron. So for non-ferrous, don't have any a little bit iron. And for the ferrous, there are two metals we covered. The first one is steel, and the second one is cast iron, which we call it alloy of the ferrous metal. And for the metallic materials, there are two types. The first one is organic, and the second one is inorganic. Okay, for the organic, we have fabric, cotton, we have wood, paper, rubber, leather, and so on. And then for inorganic materials such as minerals, cement, glass, ceramic, graphite, and so on. So let's go through for the metallic materials. The metals that build works with are divided into two general classification, which is ferrous and non-ferrous. Basically, ferrous is composed primarily of irons and irons alloy, or non-ferrous composed primarily of some element or element other than iron, and sometimes contain a small amount of ions as an alloying elements or as an impurities. So if we talk about the structure of steels, so it will divide it into two types. The first one is low alloy, and the second one which is high alloy. And for the low alloy, have a low carbon, medium carbon, high carbon, is indicate the carbon contained in the percentage of uh, iron. Okay, and then for the purpose of the difference between the metal produced, for the low carbon, there is a plain and also high strength of low alloy, and for the medium carbon planes and for the heat treatable for high carbon plane, and also used for metal for tools. And for the high alloy, the metal used for tools, and one of the very familiar, they call it stainless steel. And then we have a cast iron, which is a different type of come from the gray iron, ductile iron, white iron, malleable iron. And also we have a non-ferrous, okay, very low containing ions. We have aluminium, copper, magnesium, nickels, titanium, zinc, and its alloy. Basically, in our last chapter, we will cover this non-ferrous metal. So all those information related to this non-ferrous metal we will cover in our last chapter. And this is for the organic and inorganic, which is I already mentioned from in the previous slide. We'll go through for the ferrous metal. So basically, ferrous metal is a words derived from the Latin word is a ferrum or iron, and ferrous metal are iron-based alloy with a small percentage of carbon and other element added to achieve desirable properties. So when we change carbon content in the iron base, so it will produce different properties in terms of hardness, in terms of strength, so that by manipulating the percentage of carbon, we will get a product can suit for its application. Normally, ferrous metal are magnetic and non-ferrous metal are non-magnetic. So ferrous metals include all form of iron and steel alloy. So later on, we will see iron carbon phase diagram, so that with a certain percentage of carbon, it will produce a steel range and also cast iron range in the phase diagram. Example include wrought iron, cast iron, carbon steels, alloy steel, and tool steel. So in this term of the cast iron, carbon steel, alloy steel, and tool steel, we will cover in part 2 later on. So in this part, we will just to highlight about the difference between the term of wrought iron, which iron that has been heated and then work with tool. That's mean we work by using a tools to bend it, to make it shape, and finally to make it as a application in the decorative architectural applications such as fencing and bench frames. So basically the amount of carbon uh, impurities that put in the iron base, basically 1 to 2%, is not also carbon but also other materials such as sulfur, phosphorus, and aluminum dioxide. And for the cast iron, basically this iron that has been melted, poured into a mold and allowed to solidify. Basically the amount of 2 to 4 percentage of carbon, and also plus a small amount of silicon and manganese to make it become a cast iron. And the application is basically many parts of the product that can and limitless industrial application, such as engines parts, block, or some pen or something parts wear and tear for the automobile and other application engineering. The advantage of uh, ferrous metal uh, is come from because it's the metal is abundant quantity, so we can get easily in the earth crust and produce using relatively economical extraction, so can cut using low cost. And for the refining, alloying, and fabrication technique, a ferrous alloy is a versatile, so it will tailor to have a wide range of mechanical and physical properties. And high strength to weight ratio, perfect for usage in product that need to be a strong but lightweight. And finally, high quality and durable, and also recyclable and environmentally friendly. For the disadvantages, prone to corrosion because this ferrous metal is based of iron, and can be corrosion through rusting, with the exception of the stainless steel. Okay, when being used in machinery, the ability of ferrous metal can be affected by magnetic field because of the mostly for the ferrous metal is a magnetic. And then due to the high strength factor of the ferrous metal, they required more energy and strength to form or to rework into a required shape. So then we go for the allotropy of ions. Okay, actually, the definition of allotropy is a existence of two or more different physical forms of an chemical element. Okay, in this case, to form an allotropy is due to the effect of the temperature and pressure, and finally it will produce more than one form of crystal structure. In this case of carbon, we have several allotropy of graphite and diamond form with the existing of pressure, a different value of pressure. For graphite is hexagonal at room temperature. For the diamond, which is in form of tetrahedral at 3000 degrees Celsius at 100K atmosphere. And in case of tin, the electron of tin varies from the white tin, and also uh, has a gray tin with the atomic arrangement of a different atomic arrangement. In case of allotropy of iron, there are three forms of allotropy. The first one, alpha iron in the structure of BCC. For the gamma iron in FCC, and also the delta iron in BCC. So basically, the transformation of iron is due to the pressure, and also due to the difference of temperature. Okay, if you can see there is a range of temperature from 1540 degrees Celsius at that liquid form of iron. So and then it start to solidify, and due to the temperature decrease up to 1400 degrees Celsius, and go for the 910 degrees Celsius. Along the way, basically the liquid will change to a different form, uh, and it will show a different properties. Okay, at 1540 degrees Celsius to for 1400 degrees Celsius, the form of delta ion, and transform to the gamma ion, and also delta alpha ion. This is the same atom in every structure but having a different properties. So if we look at the graph, which is temperature versus time, so whereby the liquid form start to solidify, and to with the different temperature, uh, decrease of temperature, we can see a graph is something like this. So we start from the delta ion and down to the alpha ion. So and then we can see there is a below than 768 degrees Celsius, there is a alpha ion in the properties of magnetic. We call it ferrite. And at the 768 to 910, there is also the same alpha ion but in the non-magnetic properties. And then start at below than 1400, there is a gamma ion in the term of they call it austenite, and then delta ion and liquid ion. So in this slide we will cover of the iron carbon, which is the base metal is iron, and then a small amount of percentage impurities, which is carbon, put inside the iron. So and then it will become a different term. They call it steel and cast iron. So in case of steel, the carbon content is ranged to 0 to 2.0% of carbon. For the cast iron, basically more than 2 percentage up to 6.67%. And basically in practice, there is a range of 0.0 to 1.4% in case of steel. In case of cast iron, it less than 4.5%. So iron carbon alloy exists in two phases, basically in ferrite and cementite. Okay, in ferrite, that basically in solid solution, but in cementite there is an intermediate compound which is iron carbide resistant, whereby the combination of carbon and ferrite, which is Fe3C, and this is stable in steel only, not stable in cast iron. We call it metastable. Can decompose to be graphite and iron. Okay, this is iron carbide, iron carbide, or Fe3C phase diagram. Okay, previously from the previous chapter, we already learned about the phase diagram in different material combination. So this is iron carbide phase diagram. As you can see, the range from the 200 to 1540 degrees Celsius in terms of temperature. And we can see there is many lines occur here. So from the upper higher temperature, which is the phase diagram, is something like this. We have several amount of carbon less than 0.5. There is another phase diagram happen around here, and also we have the line of 1131 degrees Celsius, and also we have this line of 723 degrees Celsius, and we have this trench like a V shape at 0.8 and also 4.3. Okay, in this case we can see there is terms that we need to use it, get used to it in terms of alpha, gamma. Okay, and then we have a liquid. Okay, in terms of we have alpha is a ferrite. Okay, for the gamma we call it austenite, and also we have a cementite, and the combination of ferrite and cementite, there is another term. Okay, later on we will cover this. Okay, and then this carbon percentage we will there is a range from the 0 to 6.67%. Okay. Okay, from the left side, basically 0% of carbon, we call it pure iron. Okay, and for the right side, at the this line, okay, there is a 6.67% of carbon in the iron base. So at 6.67%, there is a formation of cementite, which is the formation of Fe3C. And then for the mixture of up to 2%, basically this from 0 to 2% of carbon, there is a region of steel. Okay, along the region we can see we can analyze several lines, including the line at 0.8, the line before 0.5 or something, and the line here, what will happen to the microstructure. Okay, and the rest is a cast iron region, whereas 2.0 above to 6.67 percentage of carbon. Okay, three significant region can be made relative to the steel portion of the diagram. So in this case, if we talk about the steel portion, which below than 2.0% of carbon. So if we discuss on the three line, which is E, A and B line, so we can get more information about this. Okay, in the region, the line of E, basically they call it eutectoid line, and the region of below than 0.8, 0 to 0.8% of carbon, there is a hypoeutectoid. Okay, and the region of 0.8 to 2% of carbon, which is hypereutectoid. So the line A is in the region of hypoeutectoid, and for the B line is in the region of hypereutectoid. So another term beside of gamma, alpha, and delta, there is a combination of alpha, which is ferrite, plus cementite, which is in this region. Okay, this region. So that ferrite and cementite, the term they call it perlite. Okay, perlite. And also the region of gamma plus cementite, there is also they call it perlite. Okay. Okay. After this, we will see more detail of fish diagram. Okay. The purpose of this iron carbide first diagram, we will give several information such as solid phase, invariant reaction, critical temperature, and finally eutectoid, hypereutectoid, and hypoeutectoid steel. Okay, let's discuss on the first, which is a solid phase in iron carbide phase diagram. As you can see, there is alpha ferrite, austenite, cementite, and uh, delta ferrite, which is in the solid solution. For the alpha ferrite is alpha iron. Okay, and then for the austenite, there is a gamma iron. For the cementite, which is the intermediate compound of Fe and C, which is this term, or iron carbide. And for the delta ferrite is a delta iron. So in this, for the structure, okay, uh, this BCC, and then this one is a FCC, this one is a cementite, is a orthorhombic, and for the delta ferrite is a BCC, different lattice parameter than the alpha ferrite. So the maximum solubility of carbon actually in the alpha ferrite is 0.025. Okay, call it here, this region, alpha ferrite. Okay, this intersection point, basically the value is 0.025, less than this 0.5, so less than 1, at the temperature of 723 degrees Celsius. Okay, the carbon is slightly soluble in this alpha ion. Okay, and for the austenite, okay, in this region, 2% at 1130 or 31 here, 2%. Okay, the gamma ion much greater than alpha ion, basically. And for the cementite, actually the cementite region is around here. This is for the cementite. The value is carbon existent is 6.67%. And then for the delta ferrite, at one this region, basically. Okay, after this we will see the bigger size of this shape, and this delta ferrite is in this region at 1493 degrees Celsius. So at the value of percentage of carbon is 0.09. Okay, so this we will see this. The temperature decrease solubility of carbon is until 0.08 degrees percent at 0 degrees Celsius here. Okay, this at this, and then the decrease until 0.8 at 723 degrees Celsius. This. Okay, and finally we have a magnetic. Okay, for the alpha ferrite, basically soft and ductile, but the magnetic is highly magnetic, actually below than 768 degrees Celsius. And for the austenite is in this region, basically a soft and ductile. Okay, and then for the cementite, okay, there is a very hard and brittle. This is below than 210 degrees Celsius. And then for the other information we can get is invariant reaction. Okay, this is the close-up view of the small portion of phase diagram. Just now is at 1400 up to 1537. As you can see, there is a gamma ferrite here, and also there is a austenite, and sorry, delta, and this one is gamma plus liquid here. And then we can see several information we can get. Okay, at 119 and 1493 line here, this temperature, we can see a liquid of 0.53 percent carbon, actually at this line. Okay, basically when we project this 1493 degrees Celsius, we have a 3 point. The first one is this point, second one is this point, and third one is this point. Okay, at the liquid region, there is 0.53 percent of carbon, basically combined with delta ferrite at 0.093 here. Okay, carbon produce at austenite 0.16 at this region. Okay, austenite. Okay, and then if you can see this gamma can transform to the delta liquid here at this point. Okay, at this point of 0.09 percent carbon at 1493 degrees Celsius. Okay, okay, during solidification, okay, at delta plus liquid will transform straight away to the austenite. Okay, important. This is the region is not so important, but no ferrite will be present at room temperature. Okay, at this uh, delta ferrite is not present in the room temperature because of this is quite high temperature. Okay, and then for the eutectic reaction, actually at this point, okay, at this point, we have 4.3 percent of carbon decomposed, which is liquid. Okay, and then we have produce austenite at 2.0 carbon, and also cementite at this point, which is 6.67 percent of carbon. And at this point, the liquid deformation takes place. Liquid will transform straight away to austenite plus cementite. Okay, whereby we have the austenite and then we have cementite. Okay, this very important because we can study the cast iron. Okay, because the cast iron region is from 2.0 to this line, okay, of carbon present. And then for the eutectoid reaction at 723 degrees Celsius, which is actually this line, we can see the presence of liquid actually at austenite 0.8 percent carbon decomposed, and it will produce this point, which is 0.025 percent, and also at this point, which is 6.67 percent. Okay, at this point, we can see there is a transformation from the austenite straight away to the this form ferrite and cementite. Okay, and then there is very useful for the manufacturing and heat treatment of steel. Okay, because this is the region of steel below than 2.0 of percentage of carbon. And then another information we can get is from the critical temperature of iron carbide phase diagram. In case of pure uh, iron, we have a temperature at which structural change takes place. Okay, the pure iron happen at 910 and 1400 degrees Celsius. Okay, actually at this line and this line. Okay, these points are designated by the AR for cooling and AC for heating. Actually, A is a arrest, and R is the English name for the cooling, and C for the English name of the heating, basically the critical temperature. Okay, as you can see for the carbon steel, at point where we have a critical point, as you can see, if we varies the content of carbon percentage, the critical point is will vary also. Okay, so if the content is up to 0.8 percent in this area, 0.8%, the line A3, okay, the line A3 will change, okay, from here to here. And also we have the content of 0.8 to 2.0. The line is we call it ACM line, okay, increase line. And for all C content in 723, basically we can put as a A1 here, okay, which is A1 is a lower critical temperature, okay, and A3 and ACM is upper critical temperature, okay, here. So that from this critical temperature, if the carbon content is varies, the line of critical and upper critical we produce is something like this. And finally, we have type of plain carbon steel. Okay, the type basically refer to the eutectoid steel. Okay, whereby the eutectoid steel is at 0.8, this line. And for the hypoeutectic steel is in this region, basically is less than 0.8 percent of carbon in this region. And for the hypereutectoid steel, basically from 0.8 to 2. Okay, and if we analyze for the hypoeutectic steel, basically most of the commercial steel they use this recipe. Okay, and for the more than 0.4 carbon is become very brittle. Okay, so basically for the steel is up to 2, but in the practice basically they will put the combination of 1.4 percentage of carbon. Okay, let's discuss on the development of microstructure during solidification. Okay, basically microstructure development depend on carbon content, okay, and up to 6.67 percentage of carbon, and also for the heat treatment. Basically, heat treatment is we will cover in part 2. There are several type of heat treatment, okay, including quenching, normalizing, or something. So it also depend on the very slow cooling to maintain equilibrium, and we can also observe for the three type of alloy, which is eutectoid, hypoeutectoid, and hypereutectoid in terms of its composition, so that we can see the microstructure in terms of composition. Here in the eutectoid region, whereby you can see a straight dash line here, okay, in right color at 0.8 percent of composition. So in here we can describe of a different point, which is point A, we have point B. So in case of point A, there is a region of alpha gamma phase, okay, here. there is no chain will occur at gamma phase here. Okay, along the solidification takes place, it will reach at the temperature of 723 degrees Celsius around here, and then it will reach to the perlite, whereby the alpha phase will transform to the alpha plus cementite, okay, phase, whereby we call it perlite. Okay, here. So at point B, basically consists of alternating layer of lamella. Okay, we can see from here there is a grain boundary takes place, whereby we have the gamma uh, phase, and one is cross the boundary here. It will produce cementite phase, whereby there is like a lamella stripe, something like this, of two phase. We call it perlite, formed simultaneously during transformation, has the appearance of mother pearl. Okay, this perlite, and each grain has layer oriented in same direction. If this direction, this orientation is in direction, this in this direction, and also in this direction, whereby the alpha phase has a thick light layer, this alpha phase. Okay, basically this is the alpha phase, whereby and the cementite phase has thin dark layer. This color is supposed to be dark stripe here, or lamella. Mechanical properties of the perlite basically intermediate between alpha and cementite, okay, which is ductile and hard or brittle. Okay, this is an intermediate. Okay, and the composition at 723 degrees Celsius for the alpha is basically at this point, whereby the value of the carbon content is 0.025%, and also at this point whereby the cementite at 6.67% of carbon. And if you want to look at the hypoeutectoid, which is in this red dash line here, you can see different point of C, D, E, F. So along the way we have from the gamma phase at point C, okay, at point C, which is something like this, the same as the previous slide, and then one is across at this region, whereby the existing of alpha and uh, so at point D we can see the composition. If we make a straight line here, it will cross section at this point and also this point, so we can make a projection in terms of percentage of carbon. The value is about 0.02 percentage of carbon, which is the composition is alpha, and then at this point we can make a projection is around 0.5% carbon in gamma. Okay, and when it reach to E, the alpha is phase become larger. Okay, we can see here alpha phase. Okay, the green boundary here, we can see the alpha start to nucleate, and it will start to make bigger and bigger at point E. Okay, and the composition of value of alpha and gamma, basically we can make a projection by this line, and then we have 2 point and make a projection to the composition, and we can get the value of 0.025 and also 0.8 at this point. Okay, and then start solidification from E to F. We can see a much bigger of uh, produce, produce of the containing of perlite, produce, whereby here we can see the lamella takes place, whereby the cementite, which indicate the uh, dark color, lamella start to produce. And then we have the carbon percent in alpha increase basically in line MN. This line, and carbon content of gamma increase along line MO, this line. Amount of alpha phase increases and gamma phase is decreases. As we discuss on this line and this line. At point F, basically alpha and perlite phase. This one alpha and perlite phase. And gamma from above 723 degrees Celsius will perform. This one. And then 2 perlite. This. And two type of alpha, which is eutectoid alpha and pro-eutectide alpha, which indicate in this. And for the eutectide alpha is present in perlite inside. This. And also pro-eutectide alpha is formed above 723 degrees Celsius. And if we discuss on the hyper-eutectoid, please consider this line. This line. And we can discuss on the different point at G, H, and I. As you can see, the formation of cementite at this start to nucleate. And finally, the Fe basically start to produce a very big cementite here along the way. So as you can see at point G and H, the gamma phase, and it will start to transform of cementite phase along the way. And cooling from G to H, the C content in gamma decrease along line PO here. Composition of cementite remain constant at this point, which is 6.67%. At point I, whereby we can see cementite and perlite phase exists, here. And gamma from above 723 degrees Celsius will be transformed to perlite. And finally, we have two type of cementite, which is eutectoid cementite and pro-eutectide cementite. We have this and this. Eutectoid cementite present in perlite, and pro-eutectide cementite form above 723 degrees Celsius. And if we can see the microstructure development on the different combination of carbon, whereby we can see at point A, B, and C, you can see quite a very different microstructure produced. At point A, whereby the value between 0 to 0.8 in the middle here, we can see the microstructure produces something like this. And once the carbon content is increased, you can see a slight difference in terms of the lamella produced. And start from the cementite here, or and then it will start to produce something like this, okay, whereby we can see very solid uh, structure produced. So hope you understand what I'm trying to explain, but this is kind of need to spend a lot of time to understand it, okay. So please this study more carefully on this phase diagram, because this is very important, okay, and very popular subject in terms of question or in the final exam. Okay, thank you very much. Bye bye.